Superiore of Pisa, where there were some PhD students like Alberto, who is also present in the audience, Jasen, who is a postdoc there, now I moved to China, and Leonardo Mazza, who moved to Economy in Paris, Oscar Viruela, my PhD student in Madrid, Jonathan King in St. Andrews, and Saro Fazio, who is now in Trieste. I especially acknowledge the work of Jasen and Alberto, who did most of the calculations on the hard work with this. And if you're interested, there will be also posted by Alberto tonight, so you can ask him for other details. So, the goal of my talk would be to address dissipative quantum many-body systems from a theoretical point of view. And in particular, I would like to study systems where strong interactions may drive some coherent dynamics in the system, but you are also in the presence of the coupling with the environment, which gives rise to some incoherent processes. So the point would be to understand which kind of physical mechanism can grow due to the mutual interplay or the competition between these two mechanisms. So we show that there can be a kind of competition which gives rise to a very interesting distributive results. So how is it possible to probe this kind of physics using some controllable platform? Well, nowadays there are some possibilities. One could use ultra-cold atoms or molecules by engineering the dissipation and driving these kind of systems in optical superlattices. Or one could also consider hybrid physical structures, in particular photon devices, where you can make the light interact with matter, so to generate an effect in nonlinearity. And in particular, one could think about optomechanical razor cavities or even coupled QED cavities. So here I'm not going to focus on experimental devices, but rather on the theoretical model which can describe this kind of competition. And specifically, I will try to focus on critical phenomena which may emerge in this scenario. So let me say a few words about critical phenomena. So first of all, we know that if we are at equilibrium, so without any coupling with the environment, so we know that in order to understand this kind of physics, one in principle should minimize the ground state energy if you are at zero temperature, so that by performing a free energy analysis a la Ginzburg-Landau, one is able to recover the critical behavior and phase transitions associated with many body systems. And specifically, so quantum or thermal fluctuations if you are at finite temperature may give rise to some discontinuities in the thermodynamic properties which generate the critical behavior of the system. And this can be characterized by different ordering or different symmetry in various phases which are crossed by the system. So in this context, long-range correlations are believed to be crucial in the sense that we know that typically these critical properties are ruled by the behavior of the correlation functions at long distance, while short-range correlations or the behavior of the system at short ranges is not so relevant. Now, if we go into a dissipative context, so beyond the fact that the system is in contact with some environment, path, then the situation may change. And in particular, we establish a dynamical process. And, okay, we may be interested in many things. In particular, I will focus on the possibility that the system can reach a steady state in the long-term limit. So provided the system will equilibrate to some non-equilibrium steady state, then I am going to see whether the kind of ordering which may establish in this non-equilibrium steady state has some origin which could be different from the equilibrium framework. And in particular, since here we have a dynamical process, so we have a master equation which dynamically evolves in time, that's the natural framework, it may be possible that different mechanisms will undergo this context. And specifically, I will show that short-range correlations can be important, so in some cases they may be relevant for the study of this critical phenomenon in this open system scenario. Now, let me go more into details of what I'm going to present. So our framework is about, so I'm going to study a simple model of phase transition. In particular, we focus on a Z2 symmetry breaking phase transition in the presence of dissipation. And I will employ a midfield treatment, and later I will refine it by considering cluster midfield. So we'll say a few words later. In particular, we will consider a model living on a lattice made up of many spin-1/2 particles, each on each lattice site, which can interact together and are subjected to some dissipation. In particular, we consider this model. So we take an anisotropic Heisenberg model, so that is fully anisotropic along the three x, y, z directions. It presents nearest neighbor coupling, x, x, y, y, and z, z. And there is also an incoherent part which describes some dissipative spin flips along a given direction, for example, the z-axis. So in this case, I can model the full system with the master equation having a coherent part, which is ruled by this Hamiltonian, plus a dissipative part, which involves some Lindblad operators, which correspond to sigma minus on each side of the lattice. So these Lindblad operators naturally tend to flip your spin down along this preferred z direction. So let's see whether this kind of dynamics generates the competition that I was trying to mention before. And the first thing to notice is that here it is important to have an anisotropy, because, for example, if you take a coupling along x, which is the same as the coupling along y, then your Hamiltonian system will conserve the total magnetization along this preferred z-axis. And in that case, since your Hamiltonian model is not changing the magnetization along x, along z, and the dissipation will tend to flip your spins down, your steady state will be trivially the one where all the spins are pointing down. So it is important to have this non-magnetization conserving anisotropies. This model can be implemented, experimented by means of trapped ions. So there are some proposals basically explained in this paper by Lukin and co-workers. And here they also perform a midfield study, a single-site midfield study of this model. And they draw a phase diagram at this level of the system. So they find, so this is the basic result that they find, where the different phases of the system are highlighted here as a function of the different coupling strengths of the system and for fixed dissipation strength. So one thing to notice is that this model, so the master equation of the model, presents a Z2 symmetry, since if you take sigma x and sigma y and you map them into minus sigma x and minus sigma y, so you perform a pi rotation along the z direction, then your master equation does not change. So this means that it is possible to break, probably it's possible in some cases to break this symmetry and produce some ordered phase. Like if you think in equilibrium situations, you can take an Ising model, so this is the standard mechanism which occurs in this kind of systems. But here we also have the dissipation, so we're going to see what happens. And specifically, I will not study all the phase diagram, but only consider the transition between this disordered paramagnetic phase and the symmetry broken phase, which here is highlighted with this FM or ferromagnetic phase, which implies that the magnetization of the system along the x or the y direction is different from 0 here, while it's 0 in the disordered phase. So basically like the Ising model. Now, let me first try to explain why we believe that short-range correlations can be important in this kind of scenario. So, we start with the single-site field. So we take one single spin and we couple to all the rest of the system by means of some midfield, some effective midfield, so that in practice your system, the state of the system is factorized, and you describe correlations in an effective way So of course, there are a lot of, this is a crude approximation, but still you can see what happens in this case. So we are changing the JY coupling, so the YY coupling in the Hamiltonian model, and we are fixing, so looking at this phase diagram, we are cutting along this box, performing a cutting along a vertical line. So we fix JX and Marai JY. So we see that at the single side mean field, we should find the phase transition between a disordered and an ordered phase. And indeed, if we look at the steady state magnetization along the X or the Y direction, so we see that on the left of a given critical value for the JY, the two magnetizations are zero. This is the black continuous curve and the dotted dashed curve for the two X and Y magnetizations. While on the right of this value, we are ferromagnetic in the sense that the two magnetizations are finite. So the ferromagnetic phase extends over a semi-infinite range of JY coupling values. Now, the interesting point is that if you go in the limit of JY to infinity, this magnetization goes to zero. So in the end, you will end up to be paramagnetic in this limiting case. Now, it's interesting to look at the behavior of the purity of this state in the single side level. So we just compute the trace of rho squared in the steady state and observe if whether there are some differences with respect to these phases and the paramagnetic and the ferromagnetic phase. And what we observe is that in the paramagnetic phase the purity is exactly 1. That means that the state is pure, and it is indeed the state which simply points down along the z direction. So it has a magnetization along z which is 1 and 0 along the other directions. While if you go in the ferromagnetic phase, the purity starts monotonically decreasing, and it goes to the minimum value, which is 0.5, because we are a finite system with a finite hyperspace. And in the limit of Jy, which goes to infinity, this corresponds to the completely mixed state. So it is true that the magnetization will be 0 in the infinite limit, but the structure of the state in that case would be very different with respect to this case. Indeed, on the left, this paramagnetic phase, we have a pure state, which is fully polarized, while in the infinite, in the plus infinite Jy coupling, we have a fully mixed state, which is unpolarized. So this behavior, of course, will occur only in the presence of dissipation, since here we are losing, so that the vector in the dot sphere which describes your state is shaping from length 1 to length 0 when you start going on the right. Now let's go to a slightly more complicated cluster structure, which is the 2x1 cluster. So we just consider two sides and study the system, study this small cluster embedded in all our lattice structure through the midfield coupling with the rest. And we see that the phase diagram dramatically changes, in the sense that, okay, the paramagnetic phase on the left hand is there. Then we have a ferromagnetic region which is very small as compared with that, which was a semi-infinite region. And then on the right of some certain critical value, we end up into another paramagnetic phase where the magnetization along x and y is 0. So the only region where we find finite magnetizations along the plane xy is inside here. So we notice that what happened, so that the drastic change that occurred, is that the plus Jy infinite point, which was fully mixed state in the 1x1, so single cycling field, which was indeed paramagnetic, is now moved to a finite value, which is very far from the infinity. So we opened up a full semi-infinite region, very large, where the system is paramagnetic. So we can have more insight on what is happening here by analyzing again the purity of the system, so how pure or mixed is the state. And we find out that, again, in the left paramagnetic region, which corresponds to the previous case where we were fully polarized, the purity is very close to 1. It is not exactly 1, but it is very close. So the state is nearly pure, and is pointing along Rossini, while here is finite and is decreasing, and in the right paramagnetic phase we see that the purity is very close to zero. Sorry, it's not zero because again the system is finite, so the Hilbert space is finite. But this corresponds to the fully mixed state in the 2-qubit case, 0.25. So here it's again very close to a nearly fully mixed state, like what happened before in the plus infinite case. So what happened essentially is that this point now shifted to a finite value. And let's now try to see better what happens in this 2-by-1 cluster field solution. So if we take the master equation of our system and analyze for the behavior of the expectation values of the magnetization along the three directions at the 2-by-1 midfield level, we find out this equation. So this is straightforwardly obtained by the master equation of the model. So we have some dissipative part, which is produced by dissipation of the dissipative part of the master equation, and this one is a coherent part, which is ruled by the Hamiltonian. We notice that the fact that we are considering 2-by-1 clusters and not single-site clusters will enter in these two-point correlation functions, sigma j plus 1 of the two sides inside the cluster. Now, it turns out that if you go in this side of the phase diagram, so the second paramagnetic phase, then you observe that the steady state in the 2-by-1 level is nearly factorized, but it's not exactly factorized. Indeed, if you get a factorized state, then you come back to the 1-by-1 single-site field. While here you have some corrections, so you are not exactly factorized. But it turns out that, so essentially when you calculate these expectation values, you get the product of the two expectation values plus some correction, which are the correlations inside the cluster, which are very small. Now it turns out that these correlations, despite the fact that they are very small, should drive a very completely different behavior in the system, because we observed that for the single-site field we had ferromagnetic, while for the 2-by-1 cluster we had paramagnetic. And so, basically, okay, we can rewrite this equation by writing the contribution coming from the single-site field plus the correction induced by the fact that we are considering the cluster, which involves these correlations which are very small, because we observe this nearly factorized steady state. Now, so it turns out that these are crucial, and why they are so crucial? Well, because essentially we are in a dynamical process, so we have not to look just at the ground state of a given system, but we have to look at the time relaxation of the system in time. And indeed, we can observe the following. So we said before that this is the structure of the steady state in the 2-by-1 cluster, which is very factorized. So let us slightly perturb the initial condition and consider a slightly different initial condition where we perform a simulation for a single-site field where we take the exact factorized state, so we put an equal here, and trace over one of the two qubits. So we will consider this as the initial point for the single-site field, and we see what happens. And conversely, we will consider also another case, another situation where we run the 2-by-1 clustering field algorithm by considering an initial state which is exactly the factorized state. So this is not the steady state because we have these corrections, but it is nearly the same. And we observe the following. So if we are in the ferromagnetic region, so we see that both in the single-site level and in the 2-by-1 clustering field, the time evolution of the magnetization along time will not change a lot. And this is expectable in the sense that I said that these differences between the exactly factorized and the not factorized state are very small. But this is the most important case. And so suppose to be in a situation where Jy is very large, so we are in a paramagnetic region, at least in the 2-by-1 clustering field, so we are here. And in that case, we see that if we perform a single-site mean field analysis by taking as initial condition the trace over the second spin of our 2x1 solution in the steady state, then we see that the solution drastically changes. So we plot the magnetization as a function of time, and we see that it starts from 0 because the initial solution will correspond to the 2x1 case where we don't observe symmetry breaking. But then in the end, at some time, the order of 10 in this case, it will raise up and gives rise to a symmetry broken phase. So this means that dynamics here is important in order to find out this kind of behavior at the single site level. So this kind of instability in the initial condition says that even if you are very little correlations inside the cluster, you may have enhanced changes in the steady state behavior. Now, let me briefly tell you some results which regard more larger clusters and in different dimensionalities. So we start from the one-dimensional case, so a spin chain with this kind of dissipation. And okay, of course, in 1D, the mean field is not expected to be very accurate because of the reduced dimensionality. But still, we can see some reminiscence of these mean field features, we will see. And presumably, there is also no phase transition, since essentially in one dimension, having this kind of dissipation is like being in one dimension at finding temperature, so the fluctuations induced by the dissipation or the coupling with the bath should destroy any kind of critical behavior. And indeed, this is what we observe. So if you analyze the spin ordering by analyzing the structure factor, for example, along the x direction in momentum space, and we focus on the k equal to 0 which highlights ferromagnetic ordering. So we see that, okay, here we are simulating systems of increasing length on a chain, on a closed ring, 1D up to 16 spins. And we see that the behavior of this structure factor is non-monotonic, but as long as you increase the system size, it drops to some value. And of course, we will show later how it works, how it goes. But if we just consider the mean field prediction, then if you remember, we had some critical value of Jy such that on the left side we should be paramagnetic. So in the thermodynamic limit, this structure factor should be 0, while on the right side it should be finite. Let's analyze now the behavior of these curves as a function of the length of the system. In particular, we will focus on these two peaks. So the left peak lives in the paramagnetic region according to mean field, while the right peak lives on the ferromagnetic region according to mean field. And we see that as a function of 1 over L, these correlations drop as a power law. So these data points correspond to the black points depicted here. So they were obtained by simulating our rings, finite size rings. We also perform some matrix product operator equations going to larger systems, and we coupled our matrix product operator formalism with the mean field at the borders. And quite interestingly, we see that if we are in the rightmost peak, we have this non-monotonic behavior, at least at small sizes. And this should be related to the fact that since in the blue data set we are applying the mean field at the two borders, the system here is reminiscent of the mean field coupling since it's very small. So we see this ferromagnetic reminiscence, but eventually if L goes very large, it drops again. If we analyze the decay of the correlation functions in the two cases, we see that in the left peak we have a clear exponential decay, so this is paramagnetic, while on the right point we have this non-monotonic trend, but eventually it goes to 0. So again, there is a kind of reminiscence of the ferromagnet, but still it goes to 0. Now let's go to the two-dimensional case, which maybe it's more interesting because in principle it is possible to find a phase transition between symmetric and symmetry broken phase. And let's analyze what is the fate of the single-site field predicted by Lukin and co-workers. And these are the results. So essentially we will focus on this phase space region. And we see that while the single cycling field predicts that in the upper left part the system is fully fermated, so symmetry broken, here, if you increase the cluster size in your cluster field ansatz, the extension of the ferromagnetic region shrinks. So in the single cycling field is this one. In the 2x2 cluster field, there is the appearance of these left and right paramagnetic regions, which before were not present. While in the 3x3 cluster field, we have this finite size region where the system is ferromagnetic. So we have some drastic changes in the structure of the phase diagram. And okay, here just to show that if you perform now some vertical cuts along this phase diagram, you may observe that if you take 2x2 cluster in field, you see, so they are the red curves, you see that they start from 0, then they raise up, and then they have this nomotonic behavior, which seems to signal that the state tends to destroy the magnetization but is not able to become a paramagnet. And only if you go in the 3x3 cluster, then you see that a region, a paramagnetic region here emerges. While we also see the reappearance of the ferromagnetic regions for large GY couplings that we comment in a few comments later. This is exactly the same analysis for this cut, where we also show the 4x4 cluster. And while the ferromagnetic phase is shrinking, we think that probably it will survive in the thermodynamic limit, since if you take these 3 points, basically they seem to go to some final value in the large cluster size, even if we are not able to be conclusive on that. But finally, let me focus on this rebirth of the ferromagnetic phase for large GY. And I will show, okay, just to mention, we also computed the behavior of the correlation functions, 2-point correlation functions inside the different phases. And we again see a clear exponential decay in the paramagnetic, a flat behavior in the ferromagnetic, and something intermediate here where the situation is not so clear. And last thing to say is that, as I said, here there is the reappearance of the ferromagnetic phase, but there is also some strange behavior in the 2x2 cluster here, where we see this sudden jump from 2 symmetric broken phases, which seem to point the presence of some bistabilities and metamagnetism associated with the jump. And the point is that if you now perform a linear stability analysis of your clustering field, at least in the 2x2 cluster, so you add some fluctuations over your clustering field ansatz, which are dependent on the position of the system, so they can be non-translational invariant. And then you can go to momentum space and expand these fluctuations as plane waves. And, well, you find that if you insert this in the master equation of the model, you get this behavior for the fluctuations. And if you want to check for the linear stability of the clustering field, basically you should observe that the eigenvalues of this matrix, so this one is written in the superoperator form, so these eigenvalues should be all negative if you want some linear, some stable analysis. And indeed, we see that here they are all negative, so the dark color becomes negative. This is the real part of the most unstable eigenvalue, so the largest real part of the eigenvalues of this MK matrix. And we see that here they are all negative, while in the presence of the jump we see an eigenvalue which has a 0 real part. So here the solution gets unstable for some values of the K. And the same happens when there is the rebirth of the ferromagnetic region. So it seems that this is an instability, yeah, I finished, an instability of the clustering field analysis. I think this I can skip, but at the end. So I considered a Z2-symmetry breaking phase transition, like the Ising case, and we studied different dimensionalities, provided that in 1D there is no symmetry broken phase, while in 2D probably there is this kind of physics. So the mean field results are fragile, apparently, and short-range correlations seem to be important for the emergence of this dynamical ordering. Thank you.
Questions? Do you see any model participation? I asked because I noticed that in your paper, in master equation, you participate in the eigenvectors going to underlying basis of non-interacting spins, would it be more reasonable to introduce dissipator, dissipate term to describe dissipation, in exact eigenbasis of the fully interacting system?
In the eigenbasis of the
So first you diagonalize your chain and then introduce dissipation. I would say it's more reasonable procedure.
Yeah, no.
Because if you do like sometimes you can obtain some artifacts like
I see.
non-conservation.
Analyze that actually. So we just went straight forward indeed. No, I don't know, but yeah, we can see. So you say the basis. So what we did two approaches in order to find out the steady state. So one is to numerically integrate in time master equation, and the other one is to diagonalize the Euclidean directly and to find the zero eigenstate solution of the Euclidean. But this works only for very small clusters because it's very complicated to diagonalize the Euclidean.
My question is basically how to write down
To write down? Sorry, how to write down?
to write it down.
Well, this I don't know. Yeah.
When you calculate the purity of the system, you may calculate the purity of or state of the whole system, or just the cluster.
We just take the raw steady state and we got it numerically. So we have the one single qubit or two qubit density matrix, and then we take the trace of O square. That's it. So you have exactly your raw. So you just
Assuming that the purity one is not only the state is pure, but also the state there's diagonalized or like that.
Can you repeat the question?
Yeah.
So please either use the microphone or maybe this one you can repeat the question.
Yeah, as you just calculate the purity of a small block of the first system, then the purity equals 1 also means the state is diagonalized, which is grouped into two particles like that.
Yeah, I mean, our ansatz is a cluster in field or a B field. So we do not know what happens outside, basically, because the system, we break the translational invariance by just considering this small cluster. So basically, we cannot do anything else in our approach.
If there is no question,